again. So last time, we saw the transportation problem model as this. It's the objective function, and down is the constraints for m sources and n destinations. Today, we are going to talk about the solution of the problem. Now, we introduce artificial variables z1 to zn plus n into the n plus n respective equality constraints and transfer the model into this one. Typical columns of the simplex tabulum would have the form shown in this table. Well, all entries not shown in these columns are 0. We just show the 1 and empty place are 0. Now I interpret the line 0. Okay, is the coefficient of the objective function. We move the z to the right, so the coefficient of it is -1. And the first line is the coefficient of the objective function. And this is the coefficient of the constraints. After any subsequent iteration, row 0 then would have the form shown like this, where ui and vj are the dual variables. If xij is a non-basic variable, this value, cij minus ui minus vj, is interpreted as the rate at which z will change as xij is increased. Recall that in the simplex method of linear programming problem, an initial basic feasible solution, we call it BF solution. An initial BF solution is obtained artificially by introducing artificial variables as the initial basic variables and setting them equal to Si and Dj. However, the transportation simplex method obtained the same information in much simpler ways. I want to introduce the transportation simplex method, the characteristic of it first. First, no artificial variables are needed because it is convenient to constrain an initial BF solution. I will tell you later. The second, the current law 0 can be obtained without using any other law, simply by calculating the current values of ui and vj, such that xij is a basic variable, which can be done in a straightforward way. The third, the living basic variable can be identified in a simple way without using the coefficient of the entering basic variable. And the fourth, the only information needed by the transportation simplex method is the current BF solution. The current values of ui and vj are the resulting value of this one for non-basic variable xij. If solve a TP problem by hand, it is convenient to record the information for each iteration in a transportation simplex table, as shown in table 8.15. Yeah, the table is here. Okay, let's see the structure of this table. In the middle matrix is also the cost, the unit cost. And the left is the source, right is the supply. The up is the destination, and here is demands. The demands. Here we place a law and a claim. Now we should fill the value of Vg and the corresponding Ui. Here we find that the cost we use here, and this cell we can fill xij. Iteration in a transportation simplex table. The procedure includes the 3 steps. First one is initialization. The second, optimally test. The third, iteration. For transportation problem with m sources and n destinations, the number of functional constraints is m plus n. However, for the functional constraints are equality constraints. Any one of the constraints is automatically satisfied whenever the others are satisfied. Therefore, the procedure for constructing an initial BF solution selected only need m plus n minus 1 basic variables, one at a time. Now, I'd like to introduce the first step, the initialization, which means constructing an initial BF solution. For selecting the basic variable, we present and illustrate 3 criteria here, which are the minimal cost rule and the northwest corner rule, the Vogel's approximation method. The 3 criteria and all the 3 methods to constructing an initial BF solution. So the first one, the minimal cost rule. The basic idea of it is giving priority to the model with the lowest cost per unit distributed. To make this description more concrete, I now illustrate the general procedure on the meter-watt district problem. This is the parameter matrix of the example. We now use minimal cost rule to determine the initial BF solution. With the idea of minimal cost rule, first we look all the cost and found that the minimal cost here is 0. So we allocate 50 because it can supply 50, it needs 60. So we can only give 50 to satisfy this destination. And now the supply is used out, so we can eliminate this law. Then we are looking for the minimal cost in the left matrix and found that 13 is the minimal. And how can we allocate it? Oh, it needs 50. And the supply is 50 and needs 70. So we allocate 50 to x14, and we eliminate this law. So similarly, we can find the minimal cost is 13, and here left 20. It needs 60, so we allocate 20 to this place. And now there are no demands. The demands are all satisfied, so we can eliminate this claim. Then this one do like this. Similarly, we can get just like this. So let's count. There are 1, 2, 3, 4, 5, 6, 7, 8 numbers. And m minus n is 4 plus 5. So here we get 9. 9 minus 1 is equals 8. So it can be an initial BF solution of the problem. Now let's go to the second method, northwest corner rule. Beginning by selecting x11, that is starting in the northwest corner of the transportation simplex tableau. Thereafter, if xij was the last basic variable selected, then next selected xij plus 1, that is move one claim to the right. If source I has any supply remaining, otherwise next select xi plus 1 and j. Let's move one row down. Okay. We also use these examples to illustrate this method. Okay, is the parameter matrix of the problem. First allocation is x11 with 30, which exactly uses up the demand in claim 1. So we eliminate this claim, leave a supply of 20 here. Then we select x12. The law and the claim have the same 20, 20, which allocates 20 to x22 to here, and eliminate this law and claim similarly. Then we select x12. Now the law and the claim has the same remaining, supply and demand. Then eliminate law 1 and claim 2 simultaneously. We'll allocate x22 with a circled 0 to provide a degenerate basic variable. Then go to the next x113. We found that the supply is 60 and the need is 7. So we allocate 60 to it. Okay, now continue in this manner. We eventually get the initial BF solution by the northwest corner method, or by this rule. The circled numbers are the values of the basic variables, and all the other variables and non-basic values equals to 0. The value of Z now equals the cost minus the amount of allocation, and sum all these, we get Z equals this one. Okay. For now, the third criteria, we go approximate method. The idea of this is for each law and claim remaining under consideration, calculate the arithmetic difference between the smallest and next to the smallest unit cost Cij, still remaining in that law and claim. In that law or claim, having the largest difference, select the variable having the smallest remaining unit cost. Okay, we also show this with the example. First, we calculate difference between the smallest and next to the smallest unit cost, and show as here, it's a difference. Then we find the largest difference of the law and the claim is 19. So we select the smallest cost in this claim and allocate 30, because here 30, the 50, we select a smaller one, so allocate 30 here. Then we eliminate this claim because the demand is satisfied. We get a new matrix. Also, we calculate difference between the smallest and the next to the smallest cost in the remaining matrix, and get this law and this claim. And we found that the smallest cost is 15. The biggest difference is 15. And the corresponding smallest cost is 0. So we allocate 20 to this and eliminate this law. Then we do like this, and we can get this one and this one. Okay, and then this one. Yes. Let's the initial BF solution determined by the Vogel's approximation criteria is like this. As shown in the table, there are 8 circled number cells, each corresponding to a basic variable in table, which consists of the initial BF solution. Okay, now let's summarize the general procedure for constructing the initial BF solution. First, to begin, all sources laws and destination claims of the transportation simplex tableau are initially under consideration for providing a basic variable all allocation. Second, for the law and claim still and consideration, select the next best variables according to the 3 criteria we given. The third, make that allocation large enough to exactly use up the remaining supply in its law or the remaining demand in its claim. The fourth, eliminate the law or claim from further consideration. The fifth, if only one law or only one claim remaining under consideration, the procedure is completed by selecting every remaining variable, otherwise return to step 1. Okay, that's all for the initial BF solution. Thanks.